In the next 60 minutes, you're going to learn everything you need to know about Backtesting.py, how to get started, and how to implement your own strategies. Welcome to this course. My name is Chad and I'll be your instructor. And before we get started, I think it'd be a good idea to explain a little bit about Backtesting.py, what I like about it, what I don't like about it, what it's good for, what it's not good for. So we'll start with the positives here. It's a really lightweight backtesting framework. So you might be familiar with something like VectorBT or Backtrader. And those are really great libraries, but they have lots and lots of different pieces of functionality built into them. And it gets really overwhelming and the documentation is very hard to read because there's so much of it. And it can all get a bit too much. Whereas Backtesting.py just focuses on the essentials of backtrading. It doesn't try to include its own indicator library. It doesn't try and integrate with Telegram. If you want to build that stuff in, that's great. But Backtesting.py just focuses on the backtesting portion of things. It won't try and integrate with your broker. And the result of that is that the documentation is really simple and easy to understand. I'll be working through it with you over the course of this tutorial. And as well as that, it's also very, very quick, given that it's an event-driven backtester. I'll explain a little bit more about what that means later on. But you'll see the speed for yourself later on, especially when testing single strategies. They can be tested pretty much immediately. It's also got a built-in parameter optimizer if you're into that kind of thing. If you want to plot nice heat maps, Backtesting.py has got you covered here. Some things I don't like about the library is that there's no real way of trading multiple assets, at least not in the stock version here. And it also doesn't trade fractional shares, which can be a problem. And we'll see that later on when we talk about how to customize the sizing of your orders and that kind of thing. Just to show you here how small the documentation is, if I go over here, this is it. This is literally every single function in the library. You can learn pretty much all of it in an afternoon, and indeed you will over the course of this video. We'll be covering pretty much everything in here with a few different examples. It's built with frameworks that you're very familiar with, so it will be mostly interacting with either pandas data frames or NumPy arrays, just to make life a lot easier. And so let's go ahead and get started, dig into some code, and get up and running with our first strategy here. If you'd prefer a text version of this tutorial, links will be down below. So let's go ahead and get started here and start writing some code, get up and running. I'll show you how to install everything. Let's go. So just go ahead and open up any folder or workspace that you use, whatever your IDE is. I just use Vim, so I'll just be in the terminal here. And we'll want to create a virtual environment here. So however you do that in your editor, go ahead and get that set up. So virtual env venv, and then source venv bin activate. Okay, so we're in a virtual environment here, clean Python environment, so I can show you which packages we need to install. At a minimum, you're definitely going to need the backtesting package. So it should just be pip install backtesting. And that'll install all the dependencies that you need, like NumPy and pandas and whatnot. I'm also going to install a TA library here. So I'm going to install TAlib. So pip install TAlib. Now, if you have a different package that you like to use to work with technical indicators, you're more than welcome to use that. I know TAlib can be a bit hard to install sometimes. I will leave a link in the description for a tutorial on how to install it if it's something you're struggling with. It's just my preferred TA library of choice, just to calculate things like the RSI, which I'm going to be using quite a lot in this tutorial. But you're more than welcome to use any library that you want. It should work just fine. So I think with just those two libraries that we're ready to dig in here. So I'm just going to make a Python file. I'll call it example.py. And we're going to need to do some importing here. So from backtesting, we're going to need a few things. So we want to import backtest itself, We're not going to need that for now. We'll be using that to actually run the backtest later on. We'll also need strategy. That's how we're going to define our trading logic. Where do we buy? Where do we sell? That kind of thing. We need to make a strategy. If you're familiar with Backtrader, this will all be very, very familiar to you. And that's no accident. The author of this library was very influenced by Backtrader, but wanted to make a more lightweight, smoother version. And then we'll also want to grab some data. Helpfully, Backtesting.py comes with some data built in. So we can do from backtesting.test import Goog. So this has some Google price data from I think about 2006 to 2013 or something like that. So if I print Goog here, we should have some data in a nice pandas data frame. You're obviously more than welcome to pull in your own data, and I'm assuming that you'll want to if you want to use this tool meaningfully in the future. But just so that we're on the same page, we can use this data here, which comes packaged with the library. Obviously, if you bring your own data in, make sure it looks the same as this. You know, it has the open, high, low, close volume columns, and it has a date time axis. Those are the really two important features that you need to worry about. In general, you will want both the open and the close columns because of the way this library works. Is it calculates the indicators based on the close value, or at least that's what we'll be doing, and it buys based on the value of the next open candle. So if we were looking at this day's data, it would calculate the indicator based on this value, and then if it was a buy, it would buy based on the next day's open price. Backtesting libraries do differ quite a lot on how this works, so I thought I'd just mention that straight up. Okay, so now that we've got that, let's just go ahead and write out a strategy. So a strategy you'll write out as a class which extends the strategy class that we imported. So we'll have a class called RSI, and we'll call it oscillator here, so oscillator, and it'll inherit from strategy. Now there are two functions that we need to worry about here. There's an init function, and we need to pass self into that. And there's also a next function, so define next here, and we'll pass self into that as well. So these two functions are mainly what you'll be working with when defining strategies. There are ways to do things where you only use the init function here. I'll probably talk about that a bit later on, but for now, this is how we're going to be doing things. So the init function here runs, unsurprisingly, as soon as this object is created. So it runs one time at initialization. So in here, you want to try and pack things in that can be calculated straight off the bat in one big batch, and therefore can be calculated most efficiently. So for example, if you wanted to calculate the RSI, we're going to do it inside here because you can calculate the values of the RSI for the full data frame, and it's just sort of one calculation. Now, the next function here goes through each candle individually, one by one, and evaluates the criteria and then decides whether it wants to buy on the next candle. It'll make more sense once we start filling in the logic, so let's go ahead and just get started here. So in init, we'll want to define our indicator because, like I said, we can calculate the value of this indicator anyway straight off. We don't need any fancy stuff. We just need a price data frame, and we can turn that straight into the data frame for the RSI values, and that can be fed one by one into next. So I'm going to go ahead and import talib. You can import whatever you want here. So I'll import talib. And then in init here, we'll do self.rsi. So we're going to assign a class variable here. It's going to be self.rsi is equal to self.I. So I here is how we're going to build indicators within the backtesting.py framework. So it takes a couple of parameters that we need to think about. The first one is the function. So the actual function that calculates the indicator values. So in our case, that's going to be talib.rsi. For the second value here, you'll want to pass in the data. So I'm going to pass in the close price here. It'll get this data later on when we run the strategy. For right now, you just need to know it's self.data, and then you can use .open here, I suppose, if you wanted to. You could also throw in the volume or something like that. And then any other arguments that you pass in here, are going to get passed straight into this function. So for me, this is an RSI. So the RSI takes the price and a window. So you can just leave it as a number here for now. So we could say we want the RSI, and into this indicator, we're going to pass the closing price, and we're also going to pass the time window here as another variable. I'll show you how you can make your own custom indicators after this, but for now we'll just use one pre-installed from TAlib. So that's pretty much all we're going to be doing right now in this init section. We're now going to concern ourselves with the trading logic. So we've pre-calculated all of these values, and they're going to get fed one by one into next year. So what I'm going to implement here is I want a simple crossover strategy. I want when the RSI gets above a certain value, it sells. When it gets below, it buys. That's what I want. And so in order to implement that, we'll import the crossover library from Backtesting.py. It's a really helpful little function if you want to do crossover strategies. You can, of course, implement it yourself just using regular old Python. So if I do backtesting.lib import crossover, in here, we can now say if crossover self.rsi and self.upper_bound. So it's if the first series is bigger than the second series. That's essentially what crossover does here. And well, if the RSI is greater than our upper bound, well, what do we want it to do? Well, we want it to sell everything we've got. So we'll do self.position.close. Hopefully that makes sense. And then what about if the RSI goes below the lower bound? What do we do then? Well, same sort of deal here. So elif crossover and then self.lowerbound and self.rsi. Well, in this case, we just want to do a buy. So this is kind of the opposite, where the lower bound here is above the RSI. Well, we want to start buying. Now, I realize I've just used these values here, and I haven't told Backtesting.py what they are. So we can go ahead up here, and we can just define some variables here for this class. So I'm going to say upper_bound is going to be equal to 70. Let's use the traditional values here. And we'll say lower bound is equal to 30. So now this function should be able to access them in here. That's all we need for a very, very basic strategy. I know that might be information overload. There's all this weird stuff with how do you access the positions? How do you buy, sell? What are the arguments for all of this? We'll get into that later on. For right now, let's just get something up and running. So in order to actually do the backtest here, we'll set BT for backtest, and we'll set that equal to backtest. Then you want to provide the data. So for us, that's Goog here. Then provide the strategy name. So for us, that's RSI oscillator. And then we want to select the amount of cash. So I'm going to say just $10,000. And you can also select commission in here if that's something you want. I'm going to leave that out just for now and just see how the backtesting does on its own. We can then print out some stats from the backtest. So stats is equal to bt.run. And let's see how that goes. So I told you it was quick. That finished pretty much as soon as I pressed the go button there. I just forgot to print out the stats. So you can see that maybe took a second at most to initialize everything and get it running. So you can see in here things like when it started, what the end time was, how many days, exposure time, various stats. Obviously, we did way worse than a buy and hold over that time period. We had massive drawdowns, not the best strategy in the world. We can go ahead and plot it quite easily with bt.plot. I really like the plotting library that they use. It's really nice for zooming in on different things, and it gives you that Backtrader feel, but it's not like awkwardly done in a matplotlib type thing. It's in the web browser, so you can very easily interact with it. So just to let you know how this sort of screen breaks down, the red and green boxes here indicate the months. So you'll notice that this one starts on the 1st and it ends on the 30th of June there. It's the same with every other one of these boxes. It's just kind of an indication of how the stock is generally doing over time. Sometimes it can look like there isn't one of these boxes, but it's just because it's very, very small. And if you're looking for your trades, they're these sort of dashed lines here. So you can see this one was a profitable trade because the line's in green, and it started on this candle and finished on this candle. If you go up to here, you can select that particular trade. You can look at the profit and loss, the size of it. So you can see that was 27 shares of Google. This one was 33 shares of Google. This one was 24 shares of Google, so on and so forth. We can also see some stats here. So you can see what the peak of our value was, so peak of our portfolio value. You can also see the final value. So that was 157%. The max drawdown, which is down here. So we had like basically a 50% retracement during the 2008-2009 crash. And it also tells you the maximum drawdown duration here, which seems to be a very, very long time here. Basically from sort of 2008 through 2012, we were constantly in the red on this position. So depending on your style, not too nice of a strategy. And then down here, you just have the indicators. So if you're calculating lots of different indicators, they'll all appear down here. You can turn that off with an option. If you just do like plot equals false, when you're defining the indicator with the I function that we did before, you can turn that off. And here is just a volume chart if you happen to have that data. So that's just a quick summary of this dashboard if you haven't seen something like this before, just to get our bearings, figure out what's happening. I guess you can turn on and off the trades here if you want to. And so this is obviously a really, really basic backtest, but it shows you how quickly you can get up and running here in Backtesting.py with, maybe 30 lines of code. We wrote a nice little strategy here that implemented an RSI crossover. Now, that's really interesting, but there are lots of other things that we can do in this library, which are significantly more interesting. One of them, which I know people like, is looking at strategy optimization. So we have some parameters here, and in fact, we define them as class variables here. So we have the upper bound of 70 for the RSI and the lower bound of 30. I'm also going to turn this one into a parameter here. So I'll say RSI underscore window, and I'll just set that equal to 14 by default. And we'll plug it in here as self.rsi underscore window. Now what that allowed us to do is we can access them from the optimizer down here. So instead of doing bt.run, we can call bt.optimize. So bt.optimize. And in here, we can put all of our different ranges of values that we want to test for our upper and lower bounds, as well as the RSI window. So we can say upper bound is equal to range. And then let's say we want to go from 50 up to 85 in steps of 5. We do the same thing for the lower bound here, except, we don't want to go from 50 here. We want to go maybe from 10 to 45 in steps of 5. And as you might have guessed, we'll do the same thing for the RSI window here. We'll have a range of 10 to 30 in steps of 2. Now, what's really interesting about this indicator is that you can give it a particular statistic to optimize. So you can actually pick any one of these. So you can pick the Sharpe ratio, you can pick volatility. I don't know if you wanted a really volatile portfolio. You can pick any of these statistics in here, and it will attempt to simulate all the different options and find the highest value. So do be careful if you're picking something that you want it to be small. So for example, volatility. You can define custom metrics to optimize, and I'll show you how to do that in a bit. For now, let's pick the Sharpe ratio here and see what kind of functions it comes up with. So I want to maximize the Sharpe ratio. So you want to leave that as a string and just call it Sharpe ratio like that. So that should be good here. If I just go ahead and let it run, it should just work as before. So you can see it's testing 490 different combinations. Obviously, this can take a little bit longer. And if I pull it up here, apparently this is the portfolio that produces the highest Sharpe ratio out of all of the 490 it tested. Let's go look at the stats here. It's got a Sharpe ratio of 0.59, so not exactly stellar, but that's probably more indicative of our strategy rather than the abilities of this optimizer. So let's go back here. There's one more thing I'd like to show you about this optimize function here, which is really cool. I haven't seen something exactly like this before. You can apply a constraint here. So I can apply a constraint, and what that lets me do is it lets me select only a subset of these values. So for example, let's say I set the whole thing here, and I set this from 10 to 85, and this one was also from 10 to 85. Well, it makes no sense to have the upper bound bigger than the lower bound. And obviously you might have some circumstances that are a bit more complex than this one. And so what we can do is we can create a lambda function here, and that'll take in params, and we can create a function that returns true or false based on any of these parameters. So I can pick the upper bound, the lower bound, the RSI window, whatever I want. So I only want to go ahead with this backtest if param.upperbound is greater than param.lowerbound. Otherwise, this makes no sense. And so imagine if you had something more complicated. I don't know, maybe you only want to do it if the RSI window is between the two of these. There are lots of different things you can do, many different lambda functions that you can come up with here. But I thought that was an important part of the optimizer to look at, and something that differentiates a little bit from other libraries that I've seen. This way that we can easily get rid of ranges of values that we don't like, and we don't have to be too scared about passing in dodgy parameters because we can check for it here. So I'll run this again, and just to show you this works, it might do more than we did before. Yeah, it's got like 1,000 different configurations here. I'll pull up Htop here just to show you what's happening. So you can see it's using 100% of my processing power here. So hopefully the video still works. Basically, this just means it's very well multi-threaded. So it's running separate backtests on each of the cores of my computer, which means that it can efficiently use the whole thing. And we don't have to wait for it to just go one by one through the different strategies. And if you have an extremely powerful computer, you'll notice a really big difference. So what's happened here is it's picked one with an upper bound of 30 and a lower bound of 25. So basically it's only making the tiniest possible trades here. Obviously this is a massively overfit backtest because it seems to know exactly when the uptrend's coming, and it just takes a tiny amount of it and makes sure that we don't stay in the market, which reduces volatility and therefore increases the Sharpe ratio. So I bet we've got a much higher Sharpe ratio than we had before. Obviously, that's the danger of over-optimizing, basically. So I'll change this back to the way we had it before, where this was from, say, 55 to 85. This is from 10 to 45. So all that works great, and that's how you can optimize your strategy here. Now, something that I mentioned in brief a couple of minutes ago was that you can choose your own optimization function here. So it's trying to maximize the Sharpe ratio in this instance, but we can convince it to try and optimize a different parameter. As I mentioned before, you can pick any one of these, but maybe this doesn't quite sum up what you want to optimize. Maybe you want to optimize the Sharpe ratio multiplied by the Sortino ratio, or the max drawdown plus the volatility. Any metric you can think of that uses some of these stats, it'll work just fine. So how do we do that? Well, you just define it as a regular Python function up here. So we can just define a function. I'm going to call mine optim_func, and it's going to take in a variable called series, and all series is going to be is just that list of stats that we printed out. And that's what gets passed in there. So what I'm going to do is, well, the variable I want to return is the amount of equity that we have. So series, I'll copy and paste it from here just to be safe. So I want the final equity here. And then let's paste that in here. So we'll go series, you just index into it like you would any other pandas series. And I'm going to divide that by the exposure time series, and then I'll go grab the exposure time from here. So exposure time %. So this is just how long does it stay in the market. It's only in the market 2.7% of the time. So that's traditionally seen as something that's a bit safer. So what this metric is trying to do is it's trying to figure out how do we make the most money while being in the market for the least amount of time. It might not go quite to plan, but let's at least try it here. So we'll go over here, and instead of saying Sharpe ratio, we'll use optim_func and let it go. So if I go ahead and look at this here, we can see this is again one of those which does optimize the statistic, no doubt about it, but it's not quite what we had in mind, right? It's just taking one swing trade here And then obviously because this is so steep, it's only in the market for a couple of days, and that minimizes our time in the market. So thus is the danger of defining metrics, is sometimes you get what you want. So what I'm going to do here, just to make things a little bit more interesting and just show how flexible this is here, this sort of optimization function and how we can get with it, is, well, I'm going to ask for the number of trades. So what I can do is I can do if series, and then I can index back into the series, and I'm going to ask for the number of trades. And if the number of trades is less than 10, well, then return -1. So you could return minus infinity here, I suppose, if you wanted to. So this always returns a positive number, since the equity is always going to be positive. We're not using margin or anything. And the exposure time is always going to be positive because it's a percent. So if we return a negative number, that's guaranteed to be the lowest. So it won't appear as the optimum value, basically. And so we're essentially just filtering out everything that doesn't have at least 10 trades here. So we can do the same thing here. So if we go to example.py and run it, it'll take a couple of seconds here, but not too bad for 420 backtests. And I bring it over here. This starts to look a lot more reasonable in terms of trading strategies. It's actually making some trades in the market. Now, I had to force its hand, obviously, to see how many trades it's actually making. So it made 17 trades. I only asked for a minimum of 10. So it showed that putting that lower bound in there sort of got it out of that local minima that it got stuck in, and it actually started to find more sensible parameter values for us. You may have seen there while I was back in this section that every time you run a simulation with new variables here, so you can see, it prints out the different ones. It creates for you a HTML file which you can open. So if I go into the folder here, I can just open one of these HTML files, drag it over, and this is the backtest. You've got it nice and safe here. This can be quite handy if you're running a load of backtests and then a couple of hours later you're like, what combination of variables did I use, or what did that backtest look like? This can be super handy. It's just saved as a like a regular old HTML file here. So very compatible with whatever kind of viewer you want to use. It does get kind of annoying because it tends to clog up your folder that you're using. I believe there is an option here if I go to backtests, if I go over here. Yeah, if you go over here to the plot, you can see there's going to be file name here. So you could set that to a particular folder so it doesn't clog up your entire folder that you're working in here. So that might be something to look into. You could set a file name on the plot. I'll just show you what that looks like. So if you go over here, I can make a folder, make dir plots, and then vim example.py, and I go down to bt.plot here. And then, we could do like file name equals, it's going to be like examples/plots.html, something like that. And then if I run this, that should indeed work. The folder's actually called plots, so that's why that didn't save there. So I do plots/plot.html. So you can see over here, it's running April video plot.html, and if we go into this file, it's saved it here. If you wanted to keep the same naming convention, you could do that very easily as well. So if I just get rid of this, and I'm not going to optimize things just because that takes a long time. I'll do stats is equal to bt.run, so we're just running one instance of it. There's an item in stats here, which is of particular interest to us. So you can go over here to strategy. So if I print out stats strategy, and then let's see what happens. You can see it prints out an object of type RSI oscillator here. So if I don't print out stats here, it just prints out an RSI oscillator, and you can get the parameters based on that. So like upper bound, for example, I can get that that's 70. I can get the lower bound. So you can extract all of them from stats like that, and then of course you can put that in here. So you could say lower bound is equal to this, and then just put that in the file name here. Dash lower bound, make that an F string. There you go. And that's just a little aside, how to name your different plots, how to keep them organized, stop them from clogging up your directories, etc., etc. For the remainder of this tutorial, I'll just leave it as blank, but that's just a little bit about how you can name them. So, okay. We've done some optimization here, and we've created our own unique function that we want to maximize. As this is Python, you can do literally whatever you want. You can run some crazy function on it in order to maximize whatever metric you're interested in. One other detail about Optimize that's quite helpful to know about is what happens if you've got a really wide range here of different values that you want to test. So if I ran this right now, I'd get something like 20,000 different backtests that want to try and simulate. And I mean, I could definitely sit through here and wait for the 20,000 backtests to finish, but that's really not nice. It's not optimal. So what you can do is you can set a max number of tries here. And what that's going to do is, well, if it's less than the number of possible combinations, it's going to do a randomized grid search. So instead of trying every possible combination, it'll just try the number that you tell it to. So I've told it to do 100 here. There's definitely more than 100 different combinations of these 3 different variables. So let's see what happens. I think I forgot to get rid of the .run there, maybe. Stats is equal to bt.optimize. I think it just finished really quickly because it only had to do 100 of them. And it should get a different one each time. So I'll run it a few times and then I can show you the different ones. Yeah, so if I pull these both over here. So I just ran the exact same test twice there. And yeah, I got 2 completely different backtests. And that's because it's doing only 100 different options. So I told it to do 100. And there's maybe 20,000 in here. It's picking them randomly. And obviously, if you pick them randomly, sometimes you get good ones, sometimes you get bad ones. This can be just a nice way of testing out a strategy if you don't want to do an exhaustive grid search that would take hours and hours and hours, especially while you're in development. Just using max tries here can be a really nice way to evaluate the strategy without having to do some crazy backtesting. And it also reduces the chance that you're overfitting because it's randomly selecting values rather than grid searching every possible value that you'd possibly want and finding the absolute maximum, which is almost guaranteed to be massively overfit if you're running 20,000 different simulations. So I thought that was just an important little argument here for bt.optimize that's well worth using if you want to save some time. So something that we might want to add to this optimization here to sort of make things look a bit prettier is to print out some heat maps of these different values here. So we could compare, for example, what happens as we vary the upper and lower bounds. How does that affect things? So what I'm going to do here is I'm just going to set the value of the RSI window just straight to 14, just to prove my point here in what's happening. So we've got stats, BT optimize, normal setup, except that we want to return a heat map here. So that's another fancy option of bt.optimize. It's return underscore heat map, and we'll set that equal to true. And if I go over here and we get stats, and we also want to get heat map out of this. So let's go ahead and just print out heat map here, as well as stats. And we've no need to plot this really for now. I think it didn't like that I changed the RSI window there, so I'm just going to change that back. If we go over here, let's see if it's okay now. Oh, it's actually nothing to do with that. It's the fact that I misspelled return. Good old spelling errors. You can always count on those. Return heat map. So there we go. You might notice that this looks nothing like a heat map. I actually didn't want to plot that out, so we'll go down here. Yeah, you might notice that the information that we get back here looks absolutely nothing like a heat map. Don't worry, we'll fix that in just a second here. So what we want to do to this data is just a little bit of a transform here. So what we're going to do is a regular pandas group by statement. So I'll say hm for heat map is equal to heatmap.group by. So we're going to select 2 different columns that we want to group by. So we want to group by the upper bound and the lower bound. Now, this is easier to explain once you actually see it physically. So I'm just going to type this out and then you'll see what's happening. .mean, and then I'll print out hm here. So we've got the 2 different versions here. We've got the one with 3 columns and the one with 2 columns. So essentially, what the group by statement does is it finds all unique combinations of the columns that you mention. So in our case, I mentioned the upper bound and the lower bound. If you go back to here, I mentioned explicitly the upper bound and the lower bound. So it finds all unique combinations of those, which is every single row in our case. So 55 and 10, 55 and 15, 55 and 20, so on and so forth. And then there's all these other columns here, and it bundles those together. So say if we had a 55, 10, 14, but we also had a 55, 10, 15. Well, the 14 and 15 RSIs here, those would get sort of bundled together in a group, and then to that group would apply an aggregation function. So in this case, it's the mean. So it takes whatever the average of the return was for those two values. It's just a regular pandas group by. You don't really need to worry about it in our case, to be honest. Pretty much all it's done in our example is it's just got rid of this column. If you actually compare these values, there's no change. And that's because every row has a unique combination of these two values. I'll go through some more examples in a second. It can be a bit weird to get your head around at first. Okay, so we've got that. And what I'm going to do is I'm going to unstack it. So if we print it out again, we'll now get a nice 2x2 matrix of all our different lower bound values and all our different upper bound values. And well, this can be plotted quite neatly in the Seaborn module. So you have to go and import Seaborn. If we import Seaborn as SNS, and then we go down here and we'll do sns.heatmap hm, and then we'll want to do plt.show. So this is just a thing from matplotlib that you may or may not be familiar with. We'll have to go ahead and import matplotlib as well. So import matplotlib.py plot as plt. Basically, because Seaborn uses matplotlib, we use the matplotlib way of plotting things. Not terribly important for this tutorial. This is just how you can plot single heat maps based on that information. If I let that go, we should be good. Okay, we don't have Seaborn installed. Pip install Seaborn. There we go. So if I let that run now, we should get a nice heat map. So there you go. Obviously, this is using our slightly strange custom indicator. We can bring this back to any statistic that we like. So let's find where we printed out some stats. There should be somewhere up here. There we go. So let's try and optimize for Sharp ratio, for example. We'll go down to the bottom, and instead of our optim func, we'll just use Sharp ratio. Just makes things a little bit cleaner. Same thing. Evidently, these ones here aren't making any trades, so we get just no value at all. And these ones we can see roughly where the best Sharp ratio is to be had. You can also change the coloring of the heat map. There's a nice documentation page here for matplotlib. So if you Google choosing color maps in matplotlib, you'll probably find it. It has a nice list of all of the different color maps. There are many, many, many of them that you can pick from. I'm just going to stick to some of these up here. So we could try Viridis up here. This one's quite nice, and so is Plasma. So I'll show you what those look like. So when you're plotting the heat map here in Seaborn, you say color map. So CMap is equal to Plasma. Let's try Plasma. So you can see the color scheme's slightly different there. Maybe I'll pick one that's a bit more dramatic. So I think that's how you spell that. Yep, so you can see it's sort of like a green color here. That can be important if you want to make a really pretty picture out of the parameters that you're optimizing. Okay, so that's great. We had a singular heat map here. What about if we have more than two parameters? Because a heat map is a 2D form, you can't plot more than one heat map, really. You can't plot more than two variables on a 2D shape. That just doesn't work. So what we can do is we can plot every possible combination of heat maps. So there's a nice function that comes with Backtesting.py that I'll show you here. So if I now have a range of RSI window values and I get rid of all this other heat map stuff that we did before, there's an inbuilt function that comes with it, and we can go ahead and import that. So it's from this library here that we get crossover from. It's plot_heatmaps, very memorable name. And then all you have to do is just run plot_heatmaps. Then you'll want to give it the heat map that you get from the optimizer. It understands how to read this format. You don't have to do any unstacking or anything. And you also give it an aggregation function. Now, you'll see what that does in a moment when I run it. This could take a little while depending on how many values there are, so we'll see what happens. So that's come up on my other window here. I'll drag it across. Also seems to have retained the color scheme that we last used, which is interesting. So you'll notice that there are 3 different heat maps here, and they represent all the 3 different combinations of those 3 variables. So you've got the lower bound and the upper bound, you've got the RSI window and the upper bound, and the RSI window and the lower bound. Now, what happens to the 3rd variable? Well, it averages across all of those values. So I'll explain it just for one of them, maybe it's a little bit easier to understand. So in this case, what's happened is it picks a value of upper bound, say 65, and a value of lower bound, say 35. Obviously, in our calculations, we've simulated that for a wide range of RSI values, different RSI window lengths. In this case, what happens is it takes all of those simulations where the upper bound is 65, the lower bound is 35, and the RSI can be whatever it wants, and it takes an aggregate of them. Now, we supplied the aggregation function, so I selected a mean value here. So what happens is it picks the average of all of the simulations with these upper and lower bound values. That's basically how this works here. You could provide a different aggregation function if you wanted to, of course. This can be a nice way of just thinking about how do different variables relate to each other. What happens when you vary one against another and you keep the other one constant, or you take the average of it so it's not having too much of an effect. As you get more and more variables, this gets obviously crazier and crazier because it's got to take every single pair of them. So it's going to be, your number of variables, choose 2. So if you were crazy enough to try and optimize 10 different parameters, you'd have a real struggle on your hands here. So that's pretty much everything to do with heat maps, parameter optimization, that kind of thing. That's pretty much everything in this library that covers those kinds of topics. What I'm going to move on to now is different kinds of strategies. So we're going to start looking at how we can do multi-timeframe strategies. I know that's something that a lot of people use, especially if you're using a TA-based strategy. You often want to say, look at the RSI on a weekly basis and the moving average on an hourly basis, or vice versa, or whatever you may need. So how do we implement that? Well, I'm just going to get rid of this optimization here because it's going to slow us down quite a lot. I'll just do stats is equal to bt.run and we'll print stats. So we'll not look at the plot for right now. And so we'll just go ahead and reevaluate how we've written this strategy here. So currently it's very simple. We have a daily RSI. Whenever that goes over the upper bound, we sell. Whenever it goes below the lower bound, we buy. Well, I want to add another RSI in here just to make sure that we're actually in an overheated period. I want to add a weekly RSI on top of the daily RSI. And I want to only buy when they're both at the values that I care about. So in order to do that, we'll have to import another function from the backtesting library here. And that's going to be the resample apply. So this function is going to really help us out when it comes to finding other timeframes. And essentially how we do it is we start off with our highest resolution data. So in our case, it's going to be the RSI here, this daily RSI value. I'm going to go through and change all references to it to daily RSI, just so that we're clear on which one's which. So this is daily RSI. Perfect. Now in this init section here, we can create a weekly RSI. So let's do that. Self.weekly RSI. Well, that's going to be equal to resample apply. And then you want to give it a pandas time offset here. So for example, if you wanted hourly, it's like a capital H like that. If you wanted minutely, it's a capital T like that. There are many of these different time offsets that you can use. W is weekly, which is the one that we're going to be using. And you can also choose to anchor it on a specific day. So when we think about the weekly close, we think about Friday's values. We don't think about Monday's values. And so since we're interested in the close value here, that's what we're using. I guess if you were in crypto, maybe you'd think about Sunday as the end of the week. I'm not entirely sure how that works, but you can implement it however you want. You then want to put the function in here that you want to apply, the set of data that we're using. So it's going to be self.data.close. And then any arguments that go into the function. So for example, for us, it's going to be self.rsi_window. I'm just going to keep it like a 14-week RSI, whatever this value happens to be. I'm fine with it being the same for the daily and the weekly. Although if you wanted to put that in as another parameter and optimize it, that'd be great too. There's an example on the documentation here of pretty much what the resample apply is doing behind the scenes. It's essentially just leveraging pandas. So it's downsampling the data, then it's applying our function to it, then re-indexing back to the smaller time frame, and then doing a forward fill. Don't worry if you're not too clued up on exactly what this is doing. Thankfully, we have a library to do that all for us. All you need to know is you put your time frame in here that you want to downsample to, the function, and any arguments to it. And Backtesting.py here will magically do the rest of it for us. So that's great. We've got a daily and a weekly RSI now. So let's try and use this in our strategy here. So I only want to do a sell here if there's a crossover on the daily and the weekly is above our upper bound. So, and self.weekly RSI -1, so the most recent value. Backtesting.py uses the same indexing as Python, so -1 is the most recent one, -2 is the next most recent one, so on and so forth. That can be really helpful, like in this case, where we want the most recent value of RSI. And so we want to know if the RSI is greater than self.upper bound. And we'll close out that bracket there. So now we'll only do that buy if it's confirmed on the weekly and it has the daily crossover. We can do the exact same thing over here, but with the buying. So that will just be very similar. We'll do and self.weekly RSI. The last value of there is less than self.lower bound. And then we'll go ahead and plot this out because it can be a bit difficult to tell what's going on just from a list of stats. So here we go. It only seems to have made maybe one trade in the whole thing. So it bought here. I guess we've just put in our manual values here, hence why the strategy is not too great. We could optimize this, I'm sure, using the optimizer, and we'd get some interesting things. So all we're interested in is the strategy actually doing what we want it to do? So yes, we have a weekly RSI of less than 30 here, so that's good. And do we also have a crossover here? That is the question. So yeah, we go from, so we're at a weekly of 29.7, and then we go from 34 to 29. That triggers the buy, and then on the next opening candle, it buys the assets. And I'm sure if we were to check, it wouldn't buy if it wasn't confirmed on the right time frame, and it wouldn't sell if it wasn't confirmed on the right time frame. So not the greatest strategy in the world. It only made one trade in sort of 10 years. But again, I'm sure you could put that through the optimizer and come out with something a bit more interesting. That's just how we can use different time frames within our overall strategy. You could also do something, I don't know, say on this strategy, you could say, well, I only want to buy if there's a crossover on the daily and the weekly is less than the bound and the daily is less. So self.daily RSI, the latest value is less than self.weekly RSI -1. So you can endless combinations like that. You could also say, maybe I only want to buy if the daily has been decreasing the last day. So you could do something like this. So if the most recent value here is bigger than the next most recent value, or it's bigger than the RSI value of 2 days ago or 7 days ago, or infinite options here, I'll let you decide what exactly you want to do. That's how we can use different timeframes in our strategies. So there's a few more things that we can run through here. One thing that you also might be interested in this library is how do we do different order types? So at the minute, we've just been doing long only. We buy at this point and then we sell at this point. We don't do anything too crazy other than that. But how would we do something like reverse our position if a certain condition is met, or do 2 buys in a row, or various other options? How do we do stop loss, take profit? I'll cover that right now. So let's try and implement some kind of reversal strategy based on the daily RSI here. So we'll get rid of the weekly, we don't need it anymore. And we'll go over here and we'll simplify this. So we'll get back to how we were before. Very simple, buy and sell here. But instead of just closing our position here, let's initiate a short. So we'll do buy.sell. And then when we do a buy here, well, we want to close out any shorts that we have. So we'll do self.position.close. So let's run this and see what happens. So when the RSI goes below the lower bound, close any short positions, buy, and do the inverse over here. So if it goes above the upper bound, sell any long positions and go short. Let's just see what that looks like on a graph here. Apparently I've missed some syntax. My brackets here. Okay, so if I drag this over, we can have a little look. You'll see that every trade is connected to every single other one here. That's because every time we open a position, every time we close a position, we also open a position. You might not necessarily want this because it's giving us lots of time in the market, and we've lost 80% of our equity by the end of it. So let's see if we can follow the logic here of what's happening. So at this point, it's decided it's made a loss. So over here, the RSI is 70, so it's gone ahead and bought something. So it's had a crossover to the upside, so we know from our strategy it's bought. And it's closed out a short, I believe. It's closed out a short at a loss. The price increased, but we were shorting, so that wasn't good. And it's gone long. Then at this point here, the RSI has crossed again above 70, and so it's sold our position and gone short again. So remember, we didn't have any logic to stop it taking multiple positions or freaking out like it is right now. So this is why you've got to be careful about your trading logic. So it's taken a short position here, and then when there's a crossover to the upside again, it closes a short position and reopens the same short position, which is not exactly the behavior that we want, and I believe it's doing the same thing here. So let's try and fix that and see if it mildly improves the performance of our portfolio here. So what's happening? This crossover is happening. It's closing the short and then taking out another short position. And that doesn't really make sense, at least not to me. So we can go back to our trusty documentation here. And if we go to the position class here, there's a nice couple of variables that is long and is short. So we only want to close out here when this is a long. Otherwise, it makes no sense initiating a short when we already have a short position. So, I mean, unless you wanted to double stack them, but that's not what this is doing. That's not what we intend to do. So what we can do is we can say if self.position.is_long, well, then and only then will we close out our position and actually initiate a short. And you can do the same thing on the other side here. So we only actually want to close this and initiate a buy if we're actually short. So we'll do the same thing over here. If self.position.is_short. That'll return true or false, which, it'll give us our regular if statement here. So let's run that, see what happens. And if I pull that over, you'll notice that we've made no trades. Now that's because our logic only buys or sells anything if we already have a position. So if I look at what happens here, well, we can only buy if we already have a short position, and we can only sell if we have a long position. What about if we have no position? Nothing happens. So again, trading logic can be tricky. To fix this, fairly obvious. All we have to do is, at some point, either up here or up here, we include a little phrase like or we don't have a position, basically. And so you can implement that as or not self.position. So self.position is true, or it evaluates to true if we have some kind of position, and it evaluates to false if we don't have a position. So now if we run this backtest, we should get something more interesting. Here we go. So it should at least be initiating the right sort of things. It shouldn't be doing the same thing over and over again. So here it looks like it had a profitable long position. It engages in a short, which is unprofitable. I guess at this point, the RSI goes down to 22, so it goes in a long, but then that doesn't work out either. At least we have 70% of our money rather than 20% of our money. And the strategy appears to be working as implemented, although obviously it's not a great strategy. Again, we can worry about optimizing that later on. So that's how shorting works here. That was just a very quick example of how you can buy and sell here. I'll be showing you how to change your order sizes in a second. One thing that might be interesting to you is to print out the value of position here. So print self.position. So just before it makes any kind of trade, print out position. And we'll see what that looks like. So it's not actually very interesting here. It just has an ID basically, but we can print out different attributes of it. So I'll go back to the documentation here, and you can print out a few attributes. So say we could print out the current size, for example. The size, we can print out the percentage profit and loss at the current moment. So you can imagine building your trading logic based on these if you wanted to. Lots of things you can do like that. I guess these are right before we sell short. This is what we get. So these values should be in here somewhere. That might be interesting too, depending on what kind of things you want to build. Okay, so that's shorting. How about take profit and stop loss? Well, that's also really nicely implemented here in Backtesting.py. I'll go ahead and simplify this again back to something that's really, really easy. So we'll do this. We won't bother with any shorts just because that complicates life. I think this is what you want. This is back to our really simple buy hold strategy. But as a twist, we're going to add a take profit and a stop loss. So let's run the backtest and think about what values we might want to add for a take profit and a stop loss. So you can see here we take a 20% loss. We kind of want to avoid that. So maybe it would be a good idea to have a 10% stop loss and see how that affects the strategy. So you go in here and all you have to do is set SL, and this needs to be an actual number. So I'm going to set it to be 0.95 times the current price. What is the current price, you might ask? Well, to extract that, we can just index into the closing price data. So go to is equal to self.data.close, and then we'll just get the most recent value here. So that should now set a stop loss where I shouldn't encounter much more than a 5% loss. Obviously, the way backtesting.py works, it won't trigger the stop loss like intra-bar, intraday. If you wanted that, you'd have to use hourly data or something like that. So you might end up with a scenario where you do actually lose more than 5%. So you can see here what's happened is that the stop loss is triggered here. Yeah, there's been some strange interaction here where the buy and the stop loss happen at the same time. Can happen if you're not careful, but I guess just to see the stop loss at work here, we can zoom out and we can see that we don't really lose more than 5% on any of our trades just because of how the stop loss is working. Now, oftentimes, because of our buying conditions, well, the stop loss triggers, but it buys again immediately, so that can lead to further selling. So something that you might want to keep in mind when you're setting your stop losses. Take profits is also pretty easy to do. So it's just TP is equal to, and then you can use whatever you want in here. It doesn't have to be a multiple of price. It can be, you can add the average true range. You can add any indicator that you want. You can add a constant value. Whenever you make $10, then you take profits. Whatever it is you happen to want to need. I'm going to use 1.15 times price. So whenever we get a 15% profit, we cut and run. I'll drag that across so you can see. And now basically our profits and losses are now range bound within this region. Obviously, one might want to alter our selling tactics here because it's selling and then immediately rebuying the candle after, which is not ideal. But this was just an example to show you how stop loss and take profits work. So I'm not going to worry too much about that right now. Another thing that we might want to think about here is how do we size up our positions when we buy or when we sell? Well, we can do that pretty easily using the size parameter here in the buy. So I'll get rid of the stop loss and the take profit. We've seen how that works. And there are basically two separate ways here of using this. So you can either provide a size is equal to, say, some decimal here, so 0.1. Now, backtesting.py will interpret that as saying you want to spend 10% of your available cash on every buy here. So if I press go, we should see that on the graph, it's not buying huge positions. So we shouldn't end up with a massive payout here at the top. Whenever it gets a crossover here, it's just buying 10% of our available funds. And so obviously, this is 10% and then this is 10% of the remainder, 10% of that, so on and so forth. So you can end up with these nice little patterns here, but they're much smaller than if we go all in. By default, it just spends 100% of the available cash and buys as many shares as it can. Again, I don't think by default backtesting.py can do fractional shares, which that can be a little bit of an issue here. So we can see it's essentially buying one at a time here. So if we look at these individual trades, it's buying one share of Google at a time and then selling them all at the end here when the sell conditions are met. But because we had lots of crossovers here, the buy condition was met many, many, many times. Another way of implementing that is to, instead of giving a percentage here of the available cash, you can just tell it how many of the asset you want to buy. So again, no fractions, you have to give it an integer, but I could just say that I just want to buy one share. Every time that condition is met, I want you to buy one share, and then eventually when we get to the sell here, we just close out every single one of those positions. Let's see what that looks like. So it looks like this. Very similar to the previous one we saw here, except that every single one of these is going to have a size of 1. So it's just buying one share and then selling one share. Obviously that limits your downside, but also limits your upside. But it can be very helpful if you have some strategy that revolves around laddering into a position or some kind of dollar cost averaging. So we could modify this slightly, and instead of working on a crossover, let's just buy any time that the latest value of the RSI is smaller than the lower bound. So we take the -1 there, and that should work nicely. Of course, the lower bound is just a number, it's not a vector, so you can't index into it. This should work though. So here we go, go over here. And so now we see a lot more buying action, and just basically every time the RSI is low, we buy. So this is kind of like a funky dollar cost averaging strategy basically, where we just buy during these dips and then we sell up here. We're not in the market that much and there's not that many opportunities to trade, but you could imagine this across multiple stocks where you're hopping in and out of them. And although this is only returning 40% over the time period, we're not actually in the market very long at all. I think if we go look at the stats here, we're in the market 30% of the time, so the other 60% of the time you can find something else to do with the money. Again, just an example, but it shows how you can ladder into positions by intelligently sizing your positions. And of course, you don't have to set some kind of like straight up value for this. I mean, you could have this be a class variable in here. So you have self.position size, and then you set self.position size up here. Position size is equal to, 1. And then you can optimize that and see what it comes up with as the best possible position size for your amount of cash that you have on hand. The same goes with any of this stuff, really. I mean, you could do the same thing for this. You could say -1 times some variable and see which candle you're best off looking at. Maybe you're actually best off looking at the candle from 5 days ago. So, as with all the things I'm mentioning to you here, just keep in mind that they can pretty much all be used with the optimizer. So just have that in the back of your head there, and you can make some cool charts and cool heat maps and massively overfit things. So that was position sizing. Let's have a look at how you can extract some trades out of the final backtest here. So when we print out stats, you'll notice down here there's a thing called trades. So similar, if you remember, we got the strategy earlier and we extracted what the parameter values were, right? There's the same thing over here. This is trades. So this is a pandas data frame with all the different trades on it and lots of details about them. Just because I've noticed here, this SQN, this is the default parameter which backtesting.py optimizes by if you don't pick anything else. So if you don't pick a metric to optimize by, it uses this. You can look up exactly the formula for it in the docs. I just thought I'd mention that. So back to trades here. What I can do is I can go over here and down at the bottom, instead of printing out stats, I'll print out stats, but I'll take the trades. We'll go in here and run it. And it's going to give us this because it's too big. So let's go down here. And instead of doing that, we'll take 2_string. So we'll convert it to a big string, and that will print it all and it won't abbreviate it. We'll have to zoom out a little bit here, but we now have a very clear data frame here of all of the different trades, pretty much every metric you want to know about it, exactly when it entered and exited. We have the entry and exit as a date time object here. And you can plug this into your favorite visualization tool. If you don't like the way that backtesting.py does things, You can always export this and plug it into whatever you want. You can plug it into Excel, Power BI, and other Python scripts. Because it's open source, of course, you can modify Backtesting.py itself, or maybe you just want to keep this for some kind of historic records, feed this into another algorithm. Always worth mentioning with backtesting libraries how you can extract the actual raw trade data for whatever further analysis that you want to do. Maybe you want to work out the average duration of the trades. Many different options. One final thing I'm going to show you here is a really nice function I discovered in the documentation, and it's called bars since. So we import it from the library here. It's pretty much the last of the useful ones out of here, or at least the useful ones that I've found. So it's called bars since. And what this does is you give it some kind of condition that will return true or false, and it tells you how many bars ago it was last true. So, for example, I could go over here and I could say that, well, I only want to sell after we've had a crossover to the upside here. So the daily RSI is over the upper bound, and I want it to remain above the upper bound for 3 days, and then I want to sell. So we could use this really nice function to do that for us. Otherwise, we'd have to write out, a load of if statements. We'd have to compare, what were yesterday's values, what were the day before's values. It'd get a little bit messy, so this is a much nicer way of doing it. So we can say, and, go down here, bars since self.rsi is less than self.upper bound. So this is our condition here. I'll zoom back in. I noticed we zoomed out there. So this is our condition. So this evaluates to true or false. And so I want the daily RSI to cross over, and I want it to have been at least 3 days. So I'll say equal to 3, because then it'll trade on the 3rd day. So I want it to have been 3 days since the RSI was below the upper bound here. Just an interesting tweak on this strategy that we've got going here. And I think this bars since function has a good amount of potential if you use it in the right circumstances. So let's just verify that that's actually working. Of course, I've made a syntax error here. I need a bracket. And of course, it's called the daily RSI now, not just regular RSI. So I can go over here now. Now, evidently what's happened is that I've made some kind of mistake here because it's just not selling at all. So let's go have a look at this strategy again. Yeah, so it's because I've used a crossover and a bars since. So this only is true on the exact bar on which there's a crossover, but this is only true 3 days after there's a crossover. So you can see the problem here. In order to fix this, all I have to do is not delete everything. I have to go over here and we'll just do self.dailyRSI, pick the most recent value, -1, and that just needs to be greater than self.upper bound. I think that will do the job that we actually intended it for. Of course, I need to get my brackets right. Actually greater than upper bound. So there we go. That's something more like what you would expect. We have all these different buys here of size 1, and then we eventually sell when we get a sustained rally. So let's go over here. We can see, well, where's the crossover here? So it crosses over at this point. It crosses over on this day here, I think, this one. So over on this bar, and then 1, 2, and then on this day, well, how many bars has it been since it was less? Well, it's been 1, 2, 3. This was the last day, right? And so on this day, it triggers the buy, the sell rather, which actually occurs on this day, just because of how backtesting.py works. So that's the bars since function. It's quite nice. I like it. I can imagine some really cool scenarios and different things that you can do with it. So that brings us to the end here of this course in how to use backtesting.py. I'd highly encourage you to go look at the docs now that you've ran through most of the important features of this library. As you can see, the docs are very short, yet very well documented. So I'm sure you'll have no problem finding whatever you're after. I hope that you've had fun exploring this library and it's given you some new ideas for backtests that you can try out. I'll mention again, the text versions of this tutorial are in the description. And so with that being said, I wish you luck in your backtesting adventures and have fun.